Okay, let's see. Where did I put my pen? Here it is. Sarkis, the reason for that is because they are rounding to different numbers. And unfortunately, that's just the way it is. So, yeah. So any of you who are now, well, since I just started a new stream, you guys are going to have to click the pop out again, just so you know. So you can have the chat open at the same time. Yay, doggy. Oh, it's a GIF. Let's see it. Okay, back to chemistry. Let's see. Oh, good. Very good, Zoe. Awesome. Oh, gosh. Okay, well, I'll scroll up later just so I can have a look at all the fun. Okay, so we are done with chapter 3b now. So we are going to move on to chapter 4, which is all about electrons and electron structure. Okay, so this chapter is, let's see, the least intuitive, but perhaps one of the most important chapters we have. And just a little disclaimer here. Professor Jameson, this is kind of his favorite thing ever. He loves quantum chemistry, which is what this chapter is about. I, on the other hand, am not the biggest fan of it. It tends to be pretty confusing, and thankfully quantum physics, quantum chemistry, same thing. So this chapter is basically our kind of intro to quantum physics. But just so you know, so there's going to be a lot of information in the textbook that I am not going to worry about testing you guys on, simply because it can be pretty confusing, but also it doesn't really make a lot of sense to ask a question about some of these things. You'll see when you see the chapter that there are going to be a lot of weird shapes and a lot of stuff about waves and versus particles. All that stuff, you can worry about on your own. You can just read through it, just get a glimpse of what it is. I'm not going to test you very heavily on that sort of thing, okay? So, however, this electron structure part, that is what I'm going to be pretty big on. So we're going to learn about that. We're going to learn about both, but I would focus on the electron structure. Just to say that's kind of like we're going to be focusing on the applications of this stuff, like why we're bothering to even... Okay. Marissa, try restarting Discord maybe. Or try double-clicking my name again. Maybe that'll work. Oh no, Robert, these aren't adding. This is just kind of like, this is what we're going to be talking about today. Or rather, this chapter. I'm going to give Marissa a few seconds to see if her stuff is working. So Marissa, when you figure it out, just go ahead and type something so I can see, and then hopefully that'll work for you, and then I'll move forward with this. Alrighty, any luck, Marissa? By the way, if anyone has any questions that they thought about during the break, you can go ahead and type them out. This stuff can totally be super dynamic, so we don't have to worry about, stuff that's really... Oh, that's weird. Okay, yeah, try that, Marissa. Fortunately, what I'm going to be writing right now is not terribly, what's the word? Important? I don't want to say that, but kind of. Okay, so I'm going to just go ahead and start that. So we're going to be talking about electrons specifically. Typically, we represent electrons as little arrows like this. So, this here is an electron. We represent... Oh no. Okay. I'm going to go ahead and cancel the stream, and then I will redo it. Okay. Okay. Go ahead and try this one. Is this better for anyone? Okay, good. So I don't know what happened last time, so I'm glad that we're back. Okay, so I will erase what I have written. Yay! Okay, cool. So, like I said, I had not written anything particularly exciting to start, so cool. Hopefully everyone's back and they should be able to watch now. So, cool. So, we typically talk about electrons like this. I'm going to go ahead and just designate what these mean. Uh-oh, did it break again? Let's see. I hear a lot of people disconnecting and connecting. Let's see. Okay, everyone's typing. Go, go, go. Let's see. Still working? Okay, good. Okay, in that case, this is the electron. And this is what's called an energy level. By the way, that electron is just kind of like half of an arrow. So it's not any particular crazy shape, but it's half of an arrow. If we have a second electron, it's going to go upside down. All right, so this is just kind of what we do. This is also an electron. Second electron upside down. Okay, so we're going to be talking about how electrons are going to be reacting to certain stimuli. Alrighty, so in any given atom, we're going to have different energy levels. Alright, so these are just kind of 4 energy levels. This is just some graph. Let's say this is energy. And the x-axis doesn't mean anything. So as we go up this axis, we're increasing in energy. All right, so what's going to happen is, we're going to have some electrons. Periodically, because we exist in this universe, light rays are going to come in, and they are going to excite an electron to move up in energy. So light can come along and hit your electron and give it more energy. No. There. I'll fix it. There we go. Happy, Robert? The yellow arrow is light, yes. Okay, so light is going to come in and hit some electrons, and we're going to see that those electrons can jump up in energy. All right, so if you give them more energy, they go up in energy. That kind of makes sense, right? And then, after a bit of time, they're going to go back down again. And they are going to spit out light. So light can go in, moves the electrons around, and when the electrons relax, they go back to their first energy level, they can spit out light. All right, and it turns out that these lights that they absorb and spit out are of specific colors, which are called specific wavelengths of light. I see Robert typing. I'm going to wait just a second. What's up, Robert? Oops. Ignore that. Okay, very good. So, we can talk about light and energy. So, we're going to talk about the electromagnetic spectrum. By the way, this concept here with the light in, light out idea, if you look in the textbook, there's all those colorful fires, like there's green fire and red fire and purple fire. Those are all a result of this phenomenon. Okay, but back to this. The electromagnetic spectrum we have visible light as part of this. This is the light that we are able to see with our eyes. And we're going to have a whole bunch of different types of light. Okay? Typically, we talk about high energy over there and low energy on that side. Does anybody know of visible light what the highest energy color is? Yeah, it's... Thank you, Manuel, king of the typos. Yeah, we have violet light over there, and we're going to actually follow our rainbow. Let's see. Thank goodness these colors are arranged for me already in this order. This is our... this is visible light. Okay, we have violet at the end and red on this side. It's the colors of the rainbow that you see. And we're going to see that the red light is the lowest energy of our visible light, and the violet light, the purple light, is the highest energy. Does anybody know any other types of light that we might have? Some might include the word violet or the word red. Ultraviolet and infrared. Awesome. Okay, let's talk about those next. What's up, Sarkis? Oh, I see. Right, so we have visible light somewhere here. And we are going to have infrared light next to the red side. And we're going to have ultraviolet light. I'm going to just put UV for that. Towards the higher energy side. And right, we know that UV light is not the greatest for us, right? It causes all sorts of cancers and not very good things, sunburns, not a very friendly thing. High energy. We don't like high energy. Infrared light, on the other hand, we often observe as heat as humans. Yeah, of course we got gamma. We'll talk about, fine, Robert wants gamma, I'll put gamma in. Gamma is actually our highest, yeah, fine, okay. So you guys are going to teach for me. That's correct. In between gamma and UV, we have X-rays. Alright, smarty pants, let's see, what else do we have? What's above infrared? Hint, we have one. No, well, yes, technically, radio waves are all the way out here. Microwaves, yeah. These are the major categories of light that we have. In the highest energy, we have the gamma. And the lowest energy, we have radio waves. Those are very low energy. Sorry, let me write energy for you guys. I know I've already written it on the top, but why not? Alrighty. Pop quiz. What do waves look like? Ha, good luck writing this in the text chat. Alright, fine, I'll do it for you. Waves look... Squiggly line, that is the best way. Yeah, waves look like this, right? In mathematics, sine waves, cosine waves, they all look like this, right? We have... Ooh, Angelou's got something. Let's see what's she gonna say. Nope, nothing. Sad times. Okay, fine. Okay, so we also have something that is called the wavelength. So waves are kind of these up and down motions, the squiggly lines, right? And we can have waves that are like that, and we can have waves that are like that, where they're like really spread out, right? So this one, by the way, wavelength is abbreviated by the Greek letter lambda. Thank you, Robert. Fine. That is a beautiful image. Right. So, sorry. We have, this is also the wavelength. Okay? We notice that we have kind of a medium-ish wavelength, a really short wavelength, and a really long wavelength. And we're going to see that this really short wavelength, you can see it kind of going crazy, right? It's kind of just going like up and down and up and down and up and down. And this one is actually the high energy. And this one is the low energy. Yes, shorter is absolutely more dangerous. So, if we go back up to this lovely thing that I've drawn that Robert has posted a much better image of, although his is the opposite direction of mine, we're going to see that this is also the shortest wavelength, and this is the longest wavelength. Blame Google indeed. So, we can talk about these. Let's compare infrared and X-rays. Between infrared and X-rays, which one has the longer wavelength? Yeah. IR, infrared. Definitely has a longer wavelength, and that means it has lower energy. So I guess I was like, yeah, what's up? Are we all noticing Robert listening to Spotify instead of lecture? Can you believe it? Does the wavelength affect it? Okay. No. Wavelength does not affect the distance the wave travels. So they will go kind of the same distance, okay? So light all travels at the same speed. Okay, I'm going to answer Sarkis's question first, and then we'll go on to yours, Josh. So they don't necessarily travel any amount of distance more. The only difference is that the high energy ones are just going up and down faster. They still travel the same distance as each other. Okay? Awesome. Okay, and then Josh, yes, you can measure wavelength from actually any point on the wave that's the same. So you could do it like from like the middle of it, you could do it from the top or the bottom, whichever side. Just with this, I tried to be consistent, but since this low energy one, I didn't have another top part, I just had to do it that way. Okay, but fun fact about waves. Okay, is that all right, everyone? Oh, we got someone else's mic. Awesome. Someone else is here. Okay, cool. Any other questions on this? So, I know. I'm sure it is, so good. With stuff I could ask about this, since I'm sure that is all you guys care about, is I can ask, we could compare two types of light. I could ask you which one's higher energy, which one's lower energy, which one's longer wavelength, which one's shorter wavelength. Okay, that's pretty much all I can ask with this. So I could ask you like green light versus orange light or something like that. But that's kind of it for that section. Yes, Robert. They are in that order. So purple is the highest energy, red is the lowest energy. Okay, in that exact order. So you'll notice the way that I've drawn it, it's the opposite of a rainbow. So you start with the inside, I guess. But if you look on the one that you posted, you'll see the opposite because yours is gone where the high energy on this side and the low energy on that side. So just be aware of whichever side you're looking. Okay, so the way I drew it, purple is the one on the left, and that's the highest energy. Alrighty, any questions on this? Very good. Okay, cool. Okay. Then, back we go. So, we can see, or let's go back to our electron jumping. Alrighty. By the way, the what have I done? Oh, there we go. Oh, sorry. Okay, wavelengths, by the way, length is measured in what unit? Length in general. Meters, right. So we're going to see that these guys have typical wavelengths of meters, and these guys are going to be like picometers and nanometers. And maybe we'll even get into micrometers and millimeters. So, typically we're going to be working with light that is done in nanometers. That's our kind of standard light unit. So we're going to see that if I zap this electron with some light, it's going to move up, right? We'll make this like a little movie. Alright, so now it's chilling up here. This is called the excited state, by the way. This one was called the ground state. If this electron wants to come down, which it does, because no one likes to have high energy, it can do that. And remember that if it is going to do that, if it's going to come down, it has to spit out some light. It could also spit out, well, let's just say light, yeah. So it is now back to where it was. All right, and if I just kind of redraw the light that I had up here, we're going to see that, let me use blue. These lights are both exactly the same wavelength. So, if I put in a beam of light that is, 500 nanometers, then I'm going to get a light array of 500 nanometers out again. Alright, the reason for this is because, since this is a graph, the difference between these two perhaps is equivalent to the, not millimeters, sorry, the light, the energy that's contained within a 500 nanometer photon, beam of light. So, in order for it to go up, it has to get 500 nanometers of light. If it has to go down, it's going to release 500 nanometer photon. Alrighty, the reason for this is because, big word time, energy levels are quantized. Alright, oh my goodness. What the heck does that mean? Okay, here comes my artistry. Watch this. Let's see. Do you like my emoji? Here, I'll do it here. It'll be better. It's beautiful. Where are you thinking, dude? Someone thinking, dude. Go, go, go. Do it. Thank you, Robert. Beautiful. Beautiful, beautiful, beautiful. Oh, I forgot the eyebrows. No wonder. Okay, that's why you guys have no idea what I'm doing. There we go. Okay, so quantized, big word of the day. That is a sad light bulb, isn't it? That's just terrible. Okay. So, quantized means there is exact energy differences. So, of course, nanometers is not a unit of energy, but in Chem 101, you will learn how to convert nanometers to energy. So kind of, Angelou, yeah, this is related to, technically, it's the law of conservation of mass. Matter and energy cannot be destroyed or created, right? They could just be kind of turned into each other. So we can't lose any energy. So once we put our energy in, it just comes out. Okay, same exact amount. Alrighty? Later, you're going to understand that sometimes you can give an electron a lot of energy and it might relax a little bit at a time. And we're going to see that whatever this lambda is, that the blue one is equal to the orange one plus the red one. All right, so it could relax in multiple steps, but we're getting ahead of ourselves now. So, oh goodness, one of the dogs has come up. Okay, cool. So, that's a little bit, again, beyond our purview, but that's the idea. So we could have multiple steps. So you can get a really high energy photon coming in, excite your electron really high, and then it can come back down more slowly, and it can release multiple wavelengths of light. Okay, but we're going to see that these colors are going to be unique to each element and each atom. Okay? Fun stuff. So, big point here, energy in equals energy out. Alright? We're not going to mess with any, at least right now. Alrighty, cool. Questions on that? Again, all we're looking to understand from this part is the energy that you are giving the electron has to come out again. Okay, and it's going to be the same amount of energy that you originally put in. So whatever wavelength of light you put in, you're going to get the same wavelength of light coming out, or you're going to have multiple. Yeah, exactly. It's completely like reusable. I'll put that in quotation marks. Thankfully, we do not lose any right now. You're going to see that later you can lose energy to rotations and vibrations as soon as you go into molecules, but with individual atoms, we're good. It's all just going happy, reusable energy. Yes, Elza, it is a specific amount. So each element, each atom, is able to absorb specific wavelengths of light. All right, and then each one is also going to spit out those wavelengths of light. Yeah, so I mean, as long as you have enough energy to get. So if we're using this one, let's use purple. As long as, let's say our electron is in the ground state right here, if we give it this much energy, it's going to hop up to that second level. If we gave it this much energy, it's going to hop up to that third level. All right, but we cannot get it somewhere in between these two. We can't give it, say, like this amount or something. That's a no-no. We can only give it, in this example, we can give it this one or this one. We cannot give it anything else. Okay, and each atom, each element will have its own set of which ones it can absorb and which ones it can release. And we're going to see that the reason that a lot of these things are colorful is because of these energy differences. So if one happens to have an energy difference that is equivalent to green light, it's going to spit out green light when we give it energy. Or it's going to spit out red light if, one of those is that energy level. So this one's not allowed. Okay, or in quantum sense, we call this one forbidden. Perhaps you've seen the meme, quantum physics forbids this. That's where this comes from. So you can go from 2 to 3, but you have to already be at 2. If that makes sense, Robert, okay? You can go any of those, but if you give it the energy difference between 2 and 3 and it's not at 2, then it's not going to go anywhere. All right, time to put some numbers. All right, let's make this not so confusing, perhaps. Okay, I'm going to erase these. These arrows. Okay. Elsa, I'll get your question in just a second. So, I guess we haven't used green yet. So here we go. Let's say that this is, I'm just going to totally make up numbers, okay? Okay, so those are our energy levels, okay? Just faking things. The difference between 1 and 2 is how much energy? Someone type it out, please. Yeah, it's 2. Right. So this gap in between the first two energy levels, that's the orange one, that's 2. Sorry, let me write that in orange so we can have consistency. Okay, how about the difference between the first one and the third one? So from here to up here. Yeah, first and third, so it's 5, right? And the red one, Elsa has said, is 3. Right, between the second and the third one is 3. Alrighty, so we can give this electron, if it's down here, we can give it either 2 joules or 5 joules of energy. We cannot give it anything else. That's what I'm trying to say with this. Does that make sense? If you give this electron that I've circled 3 joules of energy, nothing is going to happen. It is not going to absorb that energy. Yes, so mystically some 13 joule energy level does not exist, so that is our not allowed. So for example, that would be between 10 joules to 13 joules. That's not allowed. Correct. In order for electrons to absorb energy, they have to get exactly the amount of energy they need. They cannot get any less or any more. Let me just erase this line. So yes, Josh, you're absolutely correct. In this case, for this circled electron, we would need to either give it 2 or 5. That is absolutely correct. Correct, Manuel. It just does not absorb them. It lets them just go straight through. Oh, I'm sorry. Elsa had a question before. Not all atoms are compatible or complementary to each other. So, if I'm understanding that correctly, the only thing that's going to be different is for different atoms. These numbers will be different. If that makes sense, Elsa. So maybe this is calcium, these 3 energy levels, but if we're looking at sodium or something, these energy levels would be different numbers. Maybe it's 8, 15, and 18 or something. Just for example. I'm again just making up numbers, but that would be the idea. Is that each different element will have different energy levels. Okay, does that make sense? Cool. Alrighty. I know this is definitely more like conceptual and strange stuff. So it's weird that, yeah, it doesn't absorb the energy if it's not the exact wavelength it needs. But that's what electrons do. That's why they're strange. That's why there's an entire field of study dedicated to them that I don't like because it's very scary and a lot of math is involved. Complex math that is very horrifying. So, yeah. I'm an organic chemist. I don't deal with this stuff really at all, so thankfully. Cool. Okay. Anyways. Cool. Do I want to talk about anything else today? Yeah, you thought sig figs were bad. Ha. Yeah, fun stuff. So, let's go ahead and end for today. I'm going to stick around a few minutes for questions from you guys, and I'll keep the recording going just in case these questions are pertinent to you. I will upload all of this stuff to YouTube and Canvas. These notes that I've drawn with all these colors are going to go onto Canvas. And I will also put links to the YouTube videos up on Canvas for you guys. Okay? Alrighty, yeah, take care, guys. Oh, crap, homework. Oh my gosh. Forget the mole, worksheet. Like, I think you guys all have, I'll give you guys all credit for that. Sarkis, we all saw it. It's too late. The damage is done. So, yes, stay safe, everyone. And don't forget, Sarkis, this is recorded, so ha. Yeah. I know. With regards to homework, I'll look at it. Let's not worry about homework right now. Yes, you can delete messages, Manuel, but it's too late for you. We've already seen everything of yours. So, yeah. I hope this platform is working for you guys. I know a lot of you are going to be using Zoom or conferences or whatever in your other classes, but I hopefully think this will not be too bad. So, okay, yeah, I'm not going to change anything, so we'll keep this going. So, alrighty. Oh yeah, pronto. Ugh. I think, Robert, we're going to be sticking this way the whole semester. But I cannot predict the future. So, at least, like, the governor has said, we're kind of going till at least May. So my guess is it's pretty much going to be the whole semester. So, yeah, no homework, Elsa. If I decide to, I'll give you stuff on Wednesday, and I'll give you instructions on how to turn it in and all that stuff. Of course. So remember, if you want to leave, you just gotta click the little disconnect button here. Of course, of course. Tiffany, I'm not sure what I'm going to be teaching next semester. Yep, bye-bye, everyone. I'm glad you had fun. Chemistry should be fun. So, Elsa, what that means is the next time you open Discord, it will automatically put you back in the main classroom. And yeah, that's all that is going to happen. So it should save the server. So as soon as you open Discord, you should have this, but it will just put you in the main classroom if you don't disconnect. That's it. Now, stay safe, everyone. Be smart. I think this went just as well as I was hoping, so I'm glad that you guys seem to like it as well. Bye-bye, everyone. Tyrone, I have just started uploading the first half. I hope. There it is. Yeah, I've started uploading that. And so the second one, I'm not sure. Let me see. Chem, what's the date, guys? 3/23, 20, part 1. Okay. Is this video made for kids? It's funny. Okay. No promotions. Okay. Okay, so that one is uploading on YouTube. Thank you guys for the date. It says 4 minutes for that, and it'll probably take me another couple minutes to put them onto Canvas, just so you know. I will link the channel name for you guys, Marissa, or I'll probably just link the videos directly, and then you can find the channel from that. Oh gosh, I've got some like really old videos from other... Okay, well, you'll see if they're there. I don't know. Okay, office hours. That was a very good question. Yeah, I think that'll be the best thing to do, Cassidy. So on Wednesday, I will come about an hour earlier and I will hang out in the main classroom. And if you guys have more questions, we can go to the office if there's anything like private you guys want to talk about. So, okay. Alrighty. Any last questions? Okay. I have some DMs from you guys. I'll come and look at those in a sec, but I don't want to open them while I am recording, so just in case there's anything private. So I will hold off for a second. Okay? Cool. I'm going to go ahead and stop streaming then. And I'm going to stop the recording.